Hello and welcome again to my physics online video lecture series. Today's video we're going to begin talking about RLC series circuits. This would be a circuit that has all three elements of a resistor, an inductor, and a capacitor present. And what we want to look at today is the idea of impedance. Now each of these elements has an associated reactance, and you may recall what that reactance is. So what is reactance? We usually use either a chi or a capital X. Chi represents for a given element the maximum voltage drop over the across the element divided by the maximum current through the element for a given element. And thus for the resistor, we basically have that chi is just equal to the resistance. For the capacitor, it's an inverse relationship with the capacitance. It's the angular frequency times the capacitance reciprocaled. And for an inductor, it is the angular frequency times the inductance, where we have defined omega to be angular frequency of the AC signal. So R and C and L are specific to the device, and then omega is specific to the AC signal that is being applied to that device. So what impedance does is it kind of combines these three terms together, but it does it kind of geometrically because of the fact that we have phasors. So recall that there are phasors. Essentially the main point here is sometimes current leads, sometimes voltage leads, and sometimes they're in sync. So with the resistor, voltage and current are in phase. With the inductor, voltage is 90 degrees ahead phase-wise compared to the current, or pi over 2 radians. And for the capacitor, the current leads the voltage, which means that the voltage is 90 degrees or pi over 2 radians behind the current. Okay, so that's the other thing to recall. Now, the reason why we need both of those things is in order to get the new term, our impedance, the impedance basically is for the circuit as a whole. It's defined similarly to the basically the reactance. Basically, you can again use that the impedance will be the maximum voltage divided by the maximum current for the circuit as a whole. And the way that we basically analyze impedance, one way of doing it, with these phasors is we can calculate the impedance using the reactances of the elements in question. Then we basically can say, all right, well, I have like a wall outlet, and so that wall outlet gives me 120 volts AC, let's say. That's the peak. So given that I have this impedance, what is the maximum current that's going to be put out? And then having determined what that maximum current is, I can kind of apply it to each of the elements in turn to figure out, using their individual reactances, to figure out what the maximum voltage drop across each of those elements will be. And I also know like when it will occur for each element because I know what the phase relations are with the current. So how do we get the impedance for the system? Like this right here, this equation, you actually use it. Typical use is that once you know what the impedance is, you can use Imax, the maximum current drawn, will be delta Vmax, the maximum output voltage, divided by the impedance. So like this is the typical way in which you will actually use this equation. And so that kind of implies that we need to determine Z, the impedance, without reference to this equation. So without reference to the above equation. In other words, this above equation is actually ultimately being used to determine the maximum current. Therefore, it can't have any other unknowns in it and still be a useful equation. So therefore, Z has to already be known to properly use this equation in this form. But that said, this is how Z is defined. So if you have a circuit and you're told, well, for this RLC circuit, there is a maximum voltage applied of 120 volts, and the maximum current drawn is 2 amps, then we know that the impedance must be 120 divided by 2, which is 60 ohms. And for what it's worth, the unit is the same as with impedance, as with reactance, and as with resistance. It is the ohm. So the point being here, yeah, we know the units are ohms. We can get that from the definition. Yeah, we've got the definition. We even may be using the definition to solve stuff, but we need another equation or expression for impedance, preferably one that is in terms of the sort of like known reactances of the elements that we're using. And in order to basically get that, what you have to do is kind of return to your phase diagrams. So let's say that I have my resistor here. Let's say that I have my inductor and my capacitor located here and here. Whoops, a little offset though. You know, at 90 degrees with respect to the resistor's voltage, and of course at 180 degrees with respect to each other. So this one might represent the capacitor, this one would be for the resistor, this one would be for the inductor, this is a right angle, this is also a right angle. If I wanted to draw in the current, I know that the current happens to be basically in the same direction on the phase diagram as the resistor will be. So in some sense this is like my I total. And if I project everything onto, let's say, this x-axis, that gives me the instantaneous values. So this right here would represent I at time t. This would represent V, resistor at time t. This one right here would represent V, capacitor at time t. And this right here would represent V, inductor at time t. Now note that the capacitor and inductor are actually in opposite directions here. Okay, so if I was going to get the total V total at this time, I would basically have to add VL plus VC plus VR kind of as vectors onto the x-axis. And so what that ends up meaning is that at time t, V total basically looks somehow like VR plus, and then you essentially have like a VL minus a VC, or a VC minus a VL at any given time. And in this particular case, VC is positive, VL is negative. Sometimes it's the other way around. Like if I were to go to a different time, I may have a different value here. I can also represent VL and VC collectively by this arrow right here. So this right here would represent VL plus VC. Since they're in opposite directions, I expect a shorter arrow, and so this right here would then represent like my VL plus VC term. And so you'll notice that that's also like, in this case it's negative, it could be positive, it could be negative. So where am I going with all of this? In order to get Z, what we want to do here is get current and voltage. Now this right here is in some sense giving me like the total voltage, and this is in some sense at X, but V total proper is just simply the addition of the R, the L, and the C voltages. And that's sort of like your max value. Imax, of course, is over here. All right, so where I'm going with this is, if I want to get the magnitude of a vector, you know that this right here can be represented as just like a V. And so if this is V max, this becomes V max. And we know that what that is the square root of the dot product of the vector with itself. But that should just look like VR squared plus VL dot VL plus VC dot VC, but we know that the VL and VC basically add like this. And so we can essentially take a dot product of those two by just calling it VL minus VC and then squaring it. Okay, so this right here will give us correctly the length of that vector. Whether we happen to have the green vector pointing up in the positive direction, whether it happens to point in a more negative direction, whatever quadrant it's in, the length of this thing is basically going to be the sum of this vector, the sum of this vector, which gives you a shorter vector, and then take the length of that vector. And that's given by this expression. Okay, but now we can invoke these, and we invoke these in such a way that we can say, therefore, Vmax is equal to essentially square root of Imax times R plus Imax times basically like chi L minus chi C squared. Okay, and so now making use of Z is Vmax over Imax. These are all squared terms, and so I can pull out an Imax from all this, like so. Now divide both sides by Imax, and we Vmax over Imax, which is square root of R squared plus the square of the difference of reactance. Or in terms of the resistance, capacitance, inductance, and circuit frequency, the impedance is given by the square root of the square of the resistance plus the square of the difference between omega times the inductance and 1 over omega times the capacitance. So that gets you your impedance, and that does it without explicitly using this equation to plug in a Vmax and an Imax. We use this equation to derive the impedance, but it's sort of like we have this impedance now in terms of things that are not Vmax or Imax, and therefore we could calculate an impedance and then use it in principle to calculate stuff like a current or a voltage. So the point of today's video was mostly just to get the impedance, not to then use it and do anything else. That's why I titled it Part 1. So obviously there will eventually be a part 2. I do want to work a quick example. All right, so let's determine the impedance at 20,000 radians per second angular frequency for a circuit which is an RLC circuit of R 120 ohms, C 5.0 millifarads, which is the same as 5 times 10 to the negative 3 farads, and L of 0.25 millihenries. That's 2.5 times 10 to the negative 4 henries. So the impedance in this case would look like the square root of, and then we have our R squared, so that is 120 ohms squared, or if you'd prefer, that's 1.2 times 10 squared in ohms squared, plus the difference of these two. And so what I actually have here is omega L, so that would be 2 times 10 to the 4 times 2.5 times 10 to the negative 4 minus 1 over, and then C is 5 times 10 to the negative 3 farads times 2 times 10 to the 4 radians per second. So these are your, this is your R squared term, this is your omega times L term, and this right here is your C times omega term. And of course this term right here is also squared, and this square root covers all of this stuff. Alright, so I'm looking at the square root of this first term is basically 1.44 times 10 to the 4. Second term here, I actually have a 10 to the 4 and I have a 10 to the minus 4, so those cancel. So I'm looking at 5 minus, and I've got 1 over 5 times 10 to the negative 3 times 2 times 10 to the 4. So 2 times 5 is 10, so we got 10 to the 5, 10 to the negative 3, so that's 1 over 10 squared, all squared. And so this is going to come out very close to that 144,000. So I've got 1.44 times 10 to the 4th power, which is 14,400. And to that I'm adding 5 minus 0.01 squared, which is 24.9. So that gives me 142. That gives me 14,424.9. If I take the square root of that, I get 120.1. So if I'm retaining significant figures, this is 120. But I'll keep the 0.1 here just to note that there is some slight difference from the resistance. We wouldn't be able to maybe measure it unless we were doing very precise measurements and we had a very steady signal system. But that's the impedance for this RLC circuit. I wanted to do a second example. This one we're doing essentially an RL circuit. So the question might be like, what if you don't have an R, an L, and a C? And the answer is it's okay if you don't have an R, an L, and a C. You might be tempted here to look at this and say no capacitance, therefore C equals 0, and then look at this equation and see, gosh, I've got a 1 over omega C. And if C is 0, then this term blows up to infinity, and so my impedance must be infinite, right? Well, that's not quite right, because remember where these terms came from. They came from this equation in which I'm looking at voltage drops across stuff. If I don't have a capacitor, then I don't have any voltage drop across the capacitor. And so this equation actually just reduces to V squared R plus VL squared. Okay, so in this case, Z is equal to, and we'll recall that this is Imax times Z is equal to Vmax, and that is V R plus VL minus VC squared and squared, and this term right here is 0. And so basically what this means is that my Z in this case will look like R squared plus chi L squared, or in other words, square root of R squared plus omega squared L squared. Okay, so now that I've done that, I can come up here and see this right here is my L value. This is 2 times 10 to the negative 2 henries. This is 75 ohms. 2000 hertz, omega is equal to 2 times pi times F, and F in this case is 2000 hertz, or 2 times 10 to the 3 hertz. So when I go to plug stuff in, what I'm going to get is that the impedance is equal to the square root of R squared, so that would be 75 ohms squared, plus 2 pi omega, so 2 pi times 2.0 times 10 to the 3 hertz, and that term has to be squared, times the omega, times the L term, which is 2 by 10 to the negative 2 henries. All right. So what does all that come to? So if we plug all these into the calculator, 75 squared, this term is 5,625 square ohms, and this term collectively, let's see, we got 2 times pi times 2000 times 0.02. So, which is 251, and if we square that, we get 63,165.4 something square ohms. So if we add those two together, 5,625 plus that, and then we take a square root, we end up getting a total impedance of about 262 ohms. So that is your total impedance for this particular inductor, this solenoid inductor resistor combination. And notice that we did that without having a capacitor in there, because we recalled that this came from voltage drops, and so if there's no capacitor, there can be no voltage drop across the capacitor. So that's all that I'm going to do in today's video. The main idea was to introduce impedance and show how to go about calculating it. Hopefully, having watched this video, you've got at least a better idea of that. Enough of a guide that when you sit down with your textbook and read through it, it makes some sense to you. And so that is it. Thanks for watching.